Hello, I'm Samita Herath and I will be presenting our work Energy-Based Self-Training and Normalization for Unsupervised Domain Adaptation. These are the highlights of our work. We propose an energy-based learning framework for unsupervised domain adaptation. In this framework, we propose an improved instance selection method for self-training on unlabeled target domain instances. Furthermore, we propose a novel normalization method to improve the existing free energy alignment for domain adaptation. We observe that by combining these techniques, we can outperform state-of-the-art unsupervised domain adaptation methods on the challenging benchmarks such as DomainNet, Office Home, and Vista by a significant margin. Here we explain the energy-based learning framework within our scope. At the core of our framework lies an energy function parameterized by a deep neural network. The energy function is designed to yield a lower value when there is high compatibility between an instance and a label. As a result, it is trained with an objective to minimize the corresponding energy function output value. We realize this by negating the logic outputs of the deep neural network while training it using the softmax cross-entropy loss. Lastly, the inference rule for the energy function is chosen with these in mind. Our work leverages a byproduct of energy-based learning known as the free energy, along with two established properties of it. First, we gain an advantage from its relationship with the marginal density of the data. This relationship explains that instances from denser regions in the data space will exhibit lower free energy scores. The next property we benefit from is a bias in the free energy scores when two domains are involved in a learning task. We use a pseudo-labeled self-training task to learn from unlabeled target domain data. And it is an important question to ask whether a given unlabeled target domain instance is good enough to be used in this self-training task. Existing methods check the prediction consistency of multiple views of the data points to decide on this. Essentially, these methods consider the conditional distribution of predictions given an input when making instance selections. To this end, we propose an additional free energy comparison building on top of the first property of free energy we discussed. With this comparison, we are able to mimic the more informative joint distribution between the data and the labels when selecting an instance for the self-training task. As for the domain alignment, we build on top of the literature using the second property of free energy, or else the free energy bias. These methods demonstrate that domain invariant representations can be learned by minimizing this free energy bias. They call this technique free energy alignment. However, we observe that free energy alignment is a challenging objective to achieve. This is mainly because free energy scores are unbounded and aligning unbounded scores is a challenging learning task. To overcome this and to achieve more stable free energy alignment, we propose a novel energy normalization method as a training objective. We coin our energy normalization method into a single module that we call SCON, and we include two such separate SCON modules for the source and the target domains separately. Overall, by combining our proposed self-training method and the normalization method, we are able to outperform state-of-the-art unsupervised domain adaptation methods by a significant margin. To justify our claims, we provide a number of ablation experiments showing the importance of our instance selection method and the normalization method. Furthermore, we provide detailed analysis including qualitative and sensitivity analysis of our method. And we provide additional experiments to show the scalability of our method into other network architectures. We thank you for your attention to our work and listening to this presentation.